Okay, so now this is the Z table. So now let me zoom in a little bit. So the yellow numbers here are the Z-score values. So here, that's what the Z here stands for. These are all of the Z-score values. And then the body of the table, so these are all area information. So again, as I said, it is in terms of a proportion and not a percentage, right? So these are all proportions here. So let's interpret what this statement means here. Entries in the body of the table represents areas under the curve between negative infinity and Z. So all this means is that given that here you see a positive, here you don't see any negative values, all of these numbers in yellow are positive. So this table doesn't give us negative Z-score information, but it's okay, we don't need it. We can actually we can extrapolate, make inferences for negative Z-scores using the positive values. So you only have positive Z-scores on this table. And then the area here, the entries in the body of the table, the area here represents the area that's between negative infinity all the way up to this positive Z-score. So that simply means that these are the areas to the left of various positive Z-scores. So that's all it means. So this table gives you, when you're looking up a Z-score, it gives you the area to the left of a positive Z-score. And when you do have a negative Z-score, you can just simply take the absolute value of that negative Z-score, look up the positive version of it, get the area, and then draw your inferences for the negative Z-score. Of course, I will demonstrate that. Okay, so the row headings here represent the first two numbers of your Z-score. And then the column headings here represent the second decimal place. So again, in the column headings, you're interested in the last numbers. 1, 2, 3, 4, 5, etc. So if I had a Z-score of, let's say, 2.45, that means my first two numbers are 2.4. So that means I'm interested in this row, 2.4. And then the second decimal place is 5. And here is the second decimal place, 5. 2.45, and then you would, in order to get the area information, you would look at the intersection of your relevant row and your relevant column, 2.45, and the area you get is 0.9929. That means that if you have a Z-score of positive 2.45, the area to the left of that Z-score is 0.9929. That means 99.29% of the curve the distribution lies to the left. So now let me go to the whiteboard here to demonstrate that. So 2.45. Okay. Well, let me draw that again. All right, 2.45. So again, I randomly chose 2.45. And then this is our distribution. So I chose positive 2.45. So again, I didn't give you any information as to what is the X variable measure, what are the units. Don't worry about it. You don't need that information. So all I gave you is that z-score is 2.45. It is a positive z-score. And that means that, let me go back to that previous page, positive z-score. That means I am to the left, or sorry, to the right of the center. Right, so I am to the right of the center. And your mu is going to be right in the center. So this is mu. And here, this simply means that the distance between the center and this particular point, where z is equal to 2.45, is 2.45 standard deviations. So this particular point along the x-axis, this particular point has a certain x value, but don't worry about that because I want to focus only on the z-scores. So this is 2.45 standard deviations away from mu. So I saw your question. I just randomly picked 2.45 just to demonstrate how we use the z-table, just a random pick from the z-table. So that just means that we are 2.5 standard deviations away from the center, in particular 2.5 standard deviations to the right of the center. And I am going to use that area information that I got from the table. It's a positive z-score, and it gives me the area to the left. And the area I got was 0.9929. So that means that the area to the left, which I'm going to mark in red, so this entire area to the left of this particular z-score is 0.9929, the area to the left. So I'm just going to mark this by saying the red area is equal to 0.9929, the area to the left of this positive z-score. So of course, we already know that when z is equal to 0, you are at the midpoint, the center of this distribution. This is where z equals 0 is. And then we know that the area to the left of the center is 50%, right? So this is the center of the distribution. When z is equal to 0, you're right in the center. The area to the left is 0.5, and the area to the right is 0.5. So the area to the left of z equals 0 is 0.5. So now let's go back to the z-table. So if I were to look up z equals 0, it is going to be 0.00, right? Because the z-table is to 2 decimal places, 0, and here's the first decimal place, and then here's the second decimal place. 0.00. So that's our z-score of 0. In that case, the area to the left is 0.5, right? Because exactly half of the curve lies to the left of that z-score. And you'll notice that in the body of the table, the smallest area you see is 0.5. You don't see anything smaller than 0.5 because that would mean that you would have a negative z-score. So let me again go back to the whiteboard. Right, so this is when z is equal to 0, right? So you have 50% that lies to the left. And if your z-score was negative, then you're moving to the left of center, right? So if your z-score is negative, you are to the left of center. So let's say that your z-score is -1. Again, I'm just randomly picking these numbers. So suppose our z-score is -1. And then what would the area be if z-score was -1? And we know that, okay, so we know that anything to the left of this middle line is 50%, and anything to the left of this line that corresponds to z equals -1 is going to be some value less than 50%, some value less than 0.5. Right, so we know that whatever this is, I mean, we already looked it up, but don't worry about it. So this is going to be some area that is less than 0.5. So now here, the fact that you don't see any values, any areas less than 0.5 in the z table simply means that it doesn't give you information for negative z-scores, right? Any areas less than 0.5 indicates a negative z-score, right? So in that case, our table, the smallest area the smallest area starts at 0.5 all the way up to 0.999. That's the largest area that you have. So the smallest area is 0.5, and you don't see any values that are less than 0.5 because it only gives us area information for positive z-scores, meaning z-scores that are on the right side of the center, meaning the area will necessarily be larger. The farther away you get from the center on the right, the larger that area to the left is going to be. Let me go back to the whiteboard, right? But if you were to move, let's say to the right, where all of the positive z-scores are, you move to the right, z-score is some positive value, then area is going to be larger than 0.5. And then the farther away you are from the center to the right, the larger the area to the left. So now we can't really look up the z-score that's equal to -1, but we can look up the z-score that's equal to +1, for instance. But now I want to go back to our example, right? So let's go back to our example where we calculated a z-score of -1.5. So that's the one that I'm going to look up on the z-table now. All right, so let me go to a new page here. So we know that this is our distribution. And our z-score was a -1. -1.5, sorry, did I say -1? -1.5. Oops, let me erase that. Z equals -1.5, right? So that's our z-score. And because it is negative, it is to the left of the center, meaning the area to the left will be some value less than 0.5, meaning my z-table or our z-table doesn't give us this area information. But it does give us the area information for z equals 1.5, and that is simply the absolute value of -1.5. So anytime you have a negative z-score, You take the absolute value and look up the positive version. So now I'm also going to mark positive 1.5 on my distribution. So let's say it's here. Z is equal to 1.5. So this is what I'm going to look up. And it will give me the area to the left of this point. So it's going to give me this entire area. So now let's go back to the Z table. So 1.5. In 2 decimal places, it's 1.50. So I'm going to look up 1.50. 1.5 is right here. And then the second decimal place is 0. So I just need to find the intersection of this column and this row. And I end up with 0.9332. So let me go back to the whiteboard, 0.9332. So I just looked up the area to the left of z-score of 1.5, positive 1.5, and I'm going to break this up into 2 separate distributions. So let's take this one, and then I'm going to set it equal to the next one. Well, of course, they are supposed to look identical, but of course, because I'm hand drawing this, they're not going to look identical. But assume that they are, oh, this is terrible. Assume that they are identical. All right, so again, equal sign means that assume they are identical to each other. So the z-score of interest to me is negative 1.5. Right, so this is of what's truly of interest to me, negative 1.5. But because my Z table doesn't give me this information, I'm going to look up instead the positive version of it, positive 1.5. And when I look up the area, so now actually let me extend the line here all the way to the top. The area to the left is going to be 0.9332, right? So this is the area I looked up. The area to the left of positive 1.50 is 0.9332. So now these two are identical to each other. And when it comes to the center, right, so this is where mu is, and this is where mu is. When it comes to the center, they are equidistant. They just happen to be in opposite directions, but they are equidistant. So this is 1.5 standard deviations away, and this is a 1.5 standard deviations away. So they are equidistant. So I'm going to mark that here. Let me actually do it in red. So I'm just going to add a little red line here and a red line here. Right? So, and then I'm just going to mark it, oops, with 2 lines here to mark that they are equidistant. So these distances are identical to each other. They are equidistant. This is, oops, this is 1.5 standard deviations away, and so is this one. They are equidistant from the center. Because they are equidistant to the center, the area information will apply to this side as well. So let me extend this line all the way to the top. So we know that the area to the left of a positive 1.5 is 0.9332. And I can use that information to get the area to the right of negative 1.5, right? So these are identical, and these 2 points, z-scores, are equidistant to the center. Because they are equidistant, this large area is exactly the same large area here. If this large area is 0.9332, so is this one, right? Because they are equidistant to the center, that means that the large area here will be identical to the large area here, and then the small area here will be identical to the small area here, right? And they're just in different sides of the center. So this is exactly the same thing that I did when I was drawing inferences, right? We first looked at what share of the population retires younger than 59, but then I was also able to get the information for what share of the population retires older than 67, what share of the population retires younger than 67. That was the same as the share of the population that retires older than 59. So it's the same idea. They are equidistant. The large areas are identical, which means that the small areas are also identical. So now in order to get the small area, I just have to take 1 and subtract the large area from it, and I get 0.0668. So this is the small areas, because remember, everything under the curve adds up to 1. If this is 0.9332, this little area is 1 minus that. Same thing here. Everything adds up to 1. This little area is 1 minus the big area. So that means that here, this is 0.0668. Right? So again, identical areas for the small areas. .0668. Okay, so now I know the area information. So let me mark the center when it comes to our question. So remember, now back to our retirement age, 63 was the mean. And 60 was 60 was 1.5 standard deviations to the left of the center. And I wanted to know what share of the population retires younger than 60, meaning what is the size of this area, right? So that was my original question. Younger than 60. So that was the question. So now I know that answer. This small area corresponds to this small area. So it is 0.0668. So the answer is that 0.0668, or 6.68% if you want to express it in terms of a percentage. Or I can also express this in terms of a probability, because 0.0668 portion of the population is contained within this area. I can say that the probability of observing an individual who retires younger than 60 is 0.0668, right? So it's the same thing. So all three things here give me the same information. The share of the population, the portion of the population is 0.0668. In terms of a percentage, it's 6.68%. And in terms of a probability, you have 0.0668 probability of observing an individual who retires younger than 60. So now, of course, I can draw inferences for this area. Is the same area, right? So 0.0668, so that's the same one. So again, I mean, I didn't draw this symmetrically, but this area, this tail is identical to this tail here. So I know that this is also 0.0668, but we don't know what the xi value is, right? All we know is that the area to the right of positive 1.5, z-score of positive 1.5 is 0.0668, but we don't know what the xi value is. Well, we can work backwards from the z-score formula to figure it out. So remember what the z-score formula looks like: xi minus mu divided by sigma x So now I can actually work backwards. So I know what the z-score is, 1.5. I'm solving for xi, I don't know what it is, minus mu, which is 63. And I know that sigma is 2. So if I work backwards, meaning cross multiply 1.5 and 2, and then add 63 to isolate xi, you would get that xi is equal to 66. So we know that this particular point along the x-axis has a z-score of positive 1.5, but also has a x value of 66. This is the point where people age 66 retire. Right, so we just solve for that. And I know that 6.68% of the population retires older than 66. And I know that 93.32% of the population retires younger than 66. I also know that 6.68% of the population retires younger than 60, and 0.9332 or 93.32% of the population retires older than 60, right? So I can also make those inferences here. So I'm just going to write those down. So share of the population that retires older than 60 is 0.9332. Share of the population that retires younger than 66 is also 0.9332. And then, of course, the share of the population that retires older than 66 is 0.0668. So again, we can draw 4 pieces of information, 4 area information from just because, again, it's symmetrical. So that's the key word here. Because it is symmetrical, we start out answering our original question, but we can also draw these inferences as well. Okay, so that is it for the Z table. So do you have any questions on how to use the Z table? All right, no questions? Okay, very good. So I will stop recording this portion of the course and I will post this on YouTube as usual.